this module is about data center Ethernet. Now you have taken Ethernet, we have been taught Ethernet in 473, all right? So I'm assuming that you know all of that, but now we'll learn something. Some of that, actually I might review it again, but then there's a lot of new stuff. So for example, what is the difference between, how is the data center Ethernet different from the Ethernet at your home? Right, all of you have Ethernet at home. Then this is a review part. Review part is we will just go over the Ethernet addresses, devices, speeds and algorithms just one more time. This is something that is taught in 473 but may not be fresh in your mind. I'm just going to do that quickly. Then enhancement is spanning tree. So spanning tree start in 473. We will see how it is changed now. Virtual LANs start in 473. We will see actually not so much change but just a review of that one. And then some extensions. Alright, so here we are starting with the quiz. And I want you to just mark true or false. Which of these statements are generally true? Now here you think about the true and false. True things, I mean basically there is no perfect true or perfect false. Okay? There is always a few exceptions here and there. With time the definition and the answers change. And therefore, what do you think is the answer today? Alright? I am going to give you the answer. The answer is all of these are false. We taught you all of these as true in 473, didn't we? Now, the reason they are false is because the world has changed since the textbooks were written. Alright? And so we will see all that, how this has changed. Ethernet is a worldwide area network now. You could have one node here and one in France and it still have Ethernet. No, basically, right? Token ring is not used, token bus is not used, CSMA-CD is not used. None of them are used anymore. Ethernet uses CSMA-CD? No. Even in your home, when you take Ethernet, there is no CSMA-CD anywhere. Ethernet bridges use spanning tree, maybe at your home, but not in the data center. Ethernet frames are 15-18 byte long, they used to be, no longer today. Ethernet does not provide any delay guarantees, they do. Ethernet has congestion control, and Ethernet has non-strict priorities. Okay, so all of that is false. Alright? And so let's begin. So see how this has all become false over time. There is no CSMA-CD in the world, I'm telling you, right? And why we teach CSMA-CD? Because it's fun to teach. If there is no math, academics don't love it. Right? If you want to write a paper, you can't write a paper. So there are lots of papers published still on fixing CSMA-CD when there is no CSMA-CD in the world. Why? Because you can write an algorithm, you can write a paper, and so on and so forth. But in the real world, nobody cares. Alright? So, basically, first of all, there is no limit on the distances. It used to be few MAC addresses, now millions of MAC addresses has to be done in the data centers. There used to be that you could have 4,000 VLANs, now we need millions of VLANs. Used to be spanning tree, now we have the rapid spanning tree and other variations. Path was determined by spanning tree, now it is traffic engineered path. Simple service, now we have rate controls and strict level and service level agreements, SLAs, which means that basically we guarantee you this much, whatever we guarantee you. Exclusive priority, now we can even give you per class quality of service. And there was no management, and here we need management and performance. Alright? So with that now you have to look forward to how the Ethernet has changed. Okay? And as you will see from the date, some of it has happened in the last 5 years. So first of all of you know how the Ethernet addresses look like. But I just want to make sure that at this time, because we are going to talk so much about Ethernet that you remember this, Ethernet addresses are 48-bit long. And this slide, by the way, I took it from my 473 class. So you were taught this. The 48-bit long, the first 24-bit indicate who made the switch or who made the device. They are called organizationally unique identifier. The first bit is 1 or 0. 0 means individual, 1 means group, 0 means universal, the second bit, and the first 1 means local. So there were local Ethernet addresses. And the reason the local Ethernet addresses came about, because in 1980, when the Ethernet was being designed, and I was there basically in the design team at Digital, There are people who are saying that this addresses that you're selecting being totally, not changing at all is not good. I really want to know that this switch is on the 4th floor in the 5th building, so I want to give it an address 5432, something like that. So that was the local mode was given to them. Nobody uses it today. But in the standard, there is a local mode. That would have been just like location-sensitive IP. So it was such a debate about whether we should have a location-based addresses or without location-based addresses. And luckily, just by luck, that the people who want globally unique addresses won. Anyway, all the broadcast addresses double all ones, and the multicast basically are defined so that you could say, for example, to all the bridges, to all the Cisco bridges, and so on and so forth. There is a multicast addresses, right? Now, before I go much into IEEE, I want you to know how IEEE works. By the way, IEEE has started doing standardization in 1980 when Ethernet was first done. And the story, basically, the way it happened is that Xerox invented the Ethernet, or the person who invented the Ethernet went to Xerox. Xerox came to digital and said, why don't we make it a standard, networking standard? And so digital, Intel, and Xerox got together and they said, okay, let's make an industry standard. So how do we make industry standard? We went to IEEE. And IEEE did not used to do anything like this before, but they started a new group called 802, February 1980. So 82. All right. So 802 new group was started, and then IBM walked in and said, no, the Ethernet is not the right thing to do. Token ring is the right thing to do. And so they started many groups. So 802.3 was Ethernet, 5 was token ring, 4 was token bus, and everybody has a number after the 802. So anyway, so all 802 star standards. So the standards are numbered as follows. If it has just 802, and after that, well, let me be clear about this. This actually statement is not correct here, dot star, because if you do computer matching, this will match even 3. So anything which starts with 802 and then doesn't have 1, 2, 3, 4, 5, whatever, they apply to all 802 standards. Token ring, Ethernet, Wi-Fi. If it has a 1, even that applies to all of them. And even 2 applies to all of them. But if it is 3, then it applies only to Ethernet, and 11 Wi-Fi, 16 WiMAX, and actually there are intermediate numbers which represent some technology which you may not care or may care. But right now these are very famous, so I just put the numbers. So there is 82.3, 4, 5, 6, 7, 8, 9, 10, 11, 17, 19. I think we are up to 23 right now. Somewhere there, okay? So 802.3 standards will apply to Ethernet only. For example, there is 802.3 BA-2010. So why BA? Little b, little a. So the standards are numbered starting with A, B, C, D, like that up to Z. When they run out of Z, then they said AA, AB, AC. When they run out of AZ, then they go to BA, BC. All right? So this standard, when it came about, by that time we had finished all A's, so BA. All right? And then the year, of course. Standards with all uppercase letters are base standards. If it is capital AB, that's different than little ab. Actually, they won't have the same standard name with uppercase and lowercase. But if some standard is uppercase, that means it is a base standard. If it is a lowercase, means this is just an extension to something else. All right? So what happens to something else is that they disappear after a time. So this is an extension to something, and so after a few years, whenever that thing is revised, this will be put into that, and this will disappear, and that will become new. Okay, so I will give you an example in a minute. For example, here is one. 802.w, little w, right? 2001 was merged with 802.1d 2004. So in 2004, when they revised d, they put that in here. Up to that point, this standard was a valid number. Now you cannot find that, basically. I mean, you can still find it, but that's not relevant. It is part of that. All right? So when you write this standard from now on, please be careful about the case. I see so many people writing papers and not knowing whether it is a capital Q or little q or capital D or little d. It hurts to people like us who were in this process when all this notation was invented. Anyway, so now that you are IEEE aware, you should use the correct thing, okay? And so the standards are like this. Only recently IEEE changed the numbering system so that they put, so for example this one, 802.1 QAU. I was involved in this standard, and at that point it was called AU, 802.1 AU. And that was the right naming up to that point, but it was not clear what is it a revision of, right? So they said, why don't you put Q right there? So now 802.1 QAU is an extension to 802.1Q, but since it has a lowercase AU, that means this extension will be valid until the Q is revised and it will be put into that standard. Alright, so now when you see 802.1Q, which is different from 802.3Q, why it is different? 802.1Q applies to whom? All of them. 802.3 will apply only to Ethernet. And generally they will, to not cause you confusion, they will probably not have the same letters. I mean, they will not have 802.1Q and 802.3Q because a lot of people anyway misspell these things. They don't know the difference between 1 and 3. They don't know the difference between little q and big Q. But sometimes it happens, so you have to be careful and you have to know exactly what you are doing. So 802.11a, B, then whatever C, D, E, F. By the way, all of the letters are there, okay, except that they are not just the transmission standards. They are for something else. So there is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, W, and then A, A, Z, and then now they are into AA series. So yes. All right. So now there was another problem that when IEEE standardized it, they chose a different address format than what was already being used by digital Xerox, and the equipment had become so popular that they could not just say, okay, forget the old equipment. So up until now, which is 33 years later, we still use the old as well as the new. Every equipment has to satisfy old as well as the new. The old standard was, which is called Ethernet. The new standard is called 802.3. The old standard has 6 bytes of destination address, source address, then 2 bytes of type field. And type indicated what is in the payload, whether it is an IP or IPX or AppleTalk packet. And if you knew the type, you can give it to the right module. Right? IEEE 802.3 selected different thing. They wanted to put a length field. There was no length field here. The way you know the length is that the CRC matched. If CRC matched, the length is right. If it didn't match, then something is wrong. It could be the length, it could be byte has an error in it. So they wanted to put a length field. So there is a length field. So what do we do with the type field? Well, they put the type field into the next layer, which was called logical link control, LLC. Now LLC has its own source, destination, and then the type field, and that type is IP, IPX. Now this type is also 2 bytes. So that type can be put here with the same numbers and so on and so forth, but you have few extra bytes here. Alright, this is called ether type. 2 bytes. 16-bit indicate what is the higher layer protocol. Alright, now one more concept is names, IDs, and locators. So names, for example, somebody's name could be John Smith, and his ID could be 012345679, which is his social security number, and then his locator, his address could be 1234 Main Street, and so on and so forth. These are 3 different ideas, 3 different ways to identify this person. We could say anyone living at 1234 Main Street, I am sending the packet to them. Or we could say I am sending the packet to John. Or I could say I am sending the packet to 012345678. What are the advantages of these? The advantage of this ID number is that the ID could be in Germany and it will get to that place. Right? Because there is no address, there is no location attached with that ID. If you move to China, your packets are delivered in China. So basically you can very easily move if you just use the ID. If you use locator, then if packets, you want to get the packets, you have to tell your correspondent that my new location is this much. Now my new location is in this different country. So that's the problem, right? And name actually is same as the ID, as long as the ID is generally globally unique. Name could not be, there could be many John Smith. Then you have to specify a John Smith who graduated from Harvard in 1974 and was, this and that, and had this color. Then we can identify that this is that John Smith, right? But the good thing about the names is they are readable by people. People can understand them, remember them, but you have to make them globally unique by some more qualifications. But anyway, IDs are generally globally unique by definition, by design. So no two people will have the same ID, same social security number. So when the addresses were being discussed for Ethernet, and I was there, and I was part of that discussion, they were discussing why don't we go with the way the IP has gone. IP has gone with the locator being your address. Sounds like location is your address, right? But the Ethernet guys, not Ethernet guys, some guys said that no, we should go with the ID as the address. And they went with that ID, luckily. So let me show you. And there is so much confusion in those days, and there is so much confusion even today. So the names are like Microsoft.com is a name, but when you put the .com, then it becomes globally unique, right? Or put .us or .cn or whatever, right? That becomes globally unique. But the IDs are your cell phone number. Your cell phone number does not depend upon the city. You can get a California cell phone number here, and you can go to any place in the world, and that phone will ring when people dial that number. It's an ID. 800 numbers an ID. Ethernet addresses are ID. All right. Your Ethernet address does not change when you take it from here to the office. Skype ID is an ID. Your Skype ID remains the same regardless of where you are, at home or office or wherever, right? VoIP phone number is an ID. If you get a VoIP phone number, that's an ID. On the other hand, wired phone numbers are locators. If you take a wired phone from this plug here and you put it in your office, it won't ring at all. And IP addresses are locators. All right. So the current recommendation is that please don't use the word addresses. Just tell me whether this is your ID or this is your locator. Because addresses are used everywhere with different meanings. All right. Having said that, recommendation, we will use the addresses currently, for this lecture and for this class because it's so common. But you understand that when we say Ethernet address or we say layer 2 address or when we say MAC addresses, those are IDs. And when we say layer 3 addresses, those are locators. All right. Next concept, fundamental concepts. What is a hub? What is a switch? And so on and so forth. So hub used to be the old device which basically connected all of the wires coming to it into a real, basically together. And so if two people spoke, both the signals went to the hub and they collided. All right. And they used CSMA-CD to back off. Right. So in the CSMA-CD days, we used to have hubs. Now you haven't bought a hub in the last 5 years, and you won't buy any more because they're not made. If you bought something 15 years ago, yes, you might have a hub. But everything that is made today is a switch. What is the difference between hub and a switch? In a switch, when you talk, your packet is completely received. If it is good, then it is buffered. If somebody else talks, their packets are also completely received. If it is good, it is buffered and forwarded, whatever. But if two people talk, they don't collide. Why not? Because you are buffering them. Right? That's why they are layer 2 devices. The hub is a layer 1 device. Layer doesn't do any buffering. The bits are just coming in, the signals, electrical signals are coming in, and they collide. Hub is a layer 1 device. A switch, or also called a bridge, is a layer 2 device. Layer 2 means it understands the MAC addresses, it understands the frames, it understands CRC, it buffers. Layer 1 doesn't understand any of that. All right. So a hub, if you connect 100 computers by a hub, if one person speaks, everybody will hear. right? So they are what we call a broadcast domain. Okay, for example, this air is broadcast domain. Whatever I am saying, everybody is hearing it, right? But if you put a bridge, then when people on the left side speak, the right side people don't hear it at all. They will hear it only if the packet needs to go there. Otherwise, the packet will be just dropped at the bridge. So the bridge separates two broadcast domains. However, no, let me say, no. So this doesn't separate two, I'm sorry, let me just redefine that word. So basically, this is a collision domain. So hubs make up a collision domain. If two people in an area connected by hub speak, they will collide. But if two people in a connected by a bridge speak, they don't collide. Right? And so, but the broadcast still get through. So if suppose somebody sends a broadcast message, says, everybody please hear me, the bridges will forward that. So the broadcast goes to the bridge. The only place it stops is at the router. The routers don't understand anything about the broadcast, and so they just throw away all the broadcast packet. They only take the unicast packet and send it. They are layer 3 devices. So routers are layer 3 devices. Now, so the broadcast will, if somebody speaks here and sends a multicast or broadcast, it will be heard by everybody. So this is called a broadcast domain. This whole thing which has no routers in it. Only thing it has is the hubs and the bridges, is a broadcast domain, and that is what is called a LAN, local area network, a layer 2 domain. Actually, that's a better name now because this is no longer local area. So it's a layer 2 domain, and a layer 2 domain is a broadcast domain. And actually, in the beginning when the bridges were invented, we called it extended LAN, and this was called a LAN. This is a local area network, and this was an extended local area network. But now the word extended is gone. This whole thing is a LAN, and this is not there at all. There is no collision, and so we don't need to distinguish anymore. Yeah.
Bridges here are same as switches, right?
Bridges same as switches, yeah. So the bridges, if you read any IEEE stuff, they have traditionally used the word bridge. And the main reason between distinction between bridge and the switch is bridges are known by default to be layer 2 devices. The switches have become confusing. You could have a layer 4 switch, layer 7 switch, layer 3 switch. So the word switch has been used by the industry to mean any layer. All right? And bridge doesn't need that justification. You cannot have a layer 7 bridge. Okay, that's the main difference. But for our purposes, we will, as long as we are in layer 2, they are same. All right? So physical layer is hub, data link layer is switch, network layer is router, and then higher layers we can call them gateways. Although that gateway terminology is not standard, so I wouldn't really emphasize that here. A repeater is also a hub. Basically, a repeater is a device that restores the data. And so this repeater is basically what we call a digital amplifier. Digital amplifier means if you send it a signal, a bit which is not really nicely formed, it will say, oh, this is a 1, and it will make a nice square pulse and send it out. So that's a repeater. Hub is a multi-port repeater, but also has a fault detection and recovery. A bridge is a data link layer device. It understands the frames. And the router is a layer 3 device, and it speaks IP and so on and so forth. All right? So now you understand the difference between two things I need you to understand. Hubs are gone from the world, so don't worry about them. Only thing is the switch and the router. Switch is a layer 2 for our purposes, and if it is a layer 3 switch, I will tell you. So a bridge and a router, let's say. Bridge is a layer 2 device, and router is a layer 3 device. Router will not forward any layer 2 broadcast. And the router needs to see an IP address before it will do anything with it. If there is no IP address in the packet, it will not touch it, because it's an IP router. Right? A Ethernet frame will be forwarded by the Ethernet switches and the bridges as far as they can, and then after that it will go to the router to go further down.